The topic for this lesson is distribution and deviation. And when we say these two words, we're talking about the distribution of data and the deviation of data. So distribution just means kind of how spread out something is. For example, if I distributed candy to our class, well, some people would get candy across the board, right? Some people might get a little bit more, some people might get fewer, but this idea of distributing is the idea of spreading data across or spreading across. So the question we're answering today is, how is data distributed? In other words, how is it spread out? And to begin this, we're going to start with this example. So it says that the heights in inches of 13 students are shown below. Plot them on the line plot. So we're going to create a line plot with x's, and we're just going to put these on this line plot. So we have 160, we have a 58, we have a 56, we have another 60, we have a 64, we have another 60, lots of 60s, we have a 62, another 60, we have a 58, we have another 60, we have a 58, we have a 62, and we have a 62. So I've now put the data on this line plot, and we can see how it's distributed or spread out. What we can see is that there's a lot of people kind of in the middle, and there's very few people as you get out close to the ends of the data. There's only one person that is 56 inches tall, one person that's 64 inches tall. And what we're gonna pay attention to is sort of the curve of this data, the curve that it takes. Again, with a lot of people in the middle and with very few people on the edges, we can kind of curve this distribution and this data. This leads us into our 4 types of distributions. So we just saw one of them. We actually just saw the very first one. We call this type of data a normal distribution. So this is our first type of distribution. And we can also call it a bell curve. You'll see why in a second. We can also call it a symmetric distribution. Okay? And the reason is because if we just remember the example we just looked at, but if we look at this histogram, our curve of our data looks something like this. We call it a bell curve because it kind of has the shape of a bell. And we call it symmetric because if we were to flip this over by itself, flip it on itself, it's pretty symmetric, right? There's a line of symmetry that's here. If it's reflected here the same way it is here. Okay? So there's one clear peak. There's one clear peak. That's what sets this apart. And that clear peak is obviously in this middle part right here. Okay? It's equally spread out on both sides. And that was our normal distribution. The second type of way that this data can be distributed is called a skewed distribution. All right, so here's the thing. This set of data also has one clear peak. And in this case, the clear peak is over here. The reason it's skewed is because the clear peak is not in the middle. It's either on the right side. The clear peak could also be on the left side. The histogram could have been flipped. The peak could have been at the bottom. Okay? This means that it is not symmetrical. It means that there's no line of symmetry. We can't fold this over itself to create the same image. So we say that it is skewed. And we can think of it as having a little tail. This part here, we like to call it the tail. Now, the way we describe the data is skew left or skew right. So skew left or skew right. In this case, since the tail is going off to the left, meaning the smaller values are off to the left side, it is skewed left. So we know we skew left when the tail goes to the left. A graph that would skew right is one where the tail of the curve, let's say we had a curve that looked like this. the tail goes to the right. Okay? So it's different than the normal distribution because although it does have one obvious peak, the peak is not in the middle. Okay? That's a skewed distribution. The next type of distribution that we have is called a bimodal distribution. And let's think about what that means. The prefix bi means 2. So as you can see in this curve, the set of data has 2 peaks. It has a peak here and it has a peak here. So this has 2 clear peaks. Okay? And then the last one is called a uniform distribution. The word uniform also just means the same. And so if we tried to draw a curve on this graph, we wouldn't even really draw a curve. It would just be kind of a flat line. So we call this a uniform distribution. This means that the data is equally spread. Okay? There's no obvious part that is higher than the other. So these are the 4 types of distribution. The normal distribution has this shape. The skewed distribution has one of these 2 shapes. A bimodal distribution has 2 peaks. And a uniform distribution is just a flat line. Now, so far we have covered measures of center. So besides its center of a set of data, which can be measured by the mean, median, or mode, another characteristic of a data set is how closely the data points are graphed. And one measure of spread is standard deviation. So this is a new topic for us. But before we continue to that, I want to make one thing clear. What we've learned so far, mean, median, and mode, we call these measures of center. Why? Because all of these have given us an idea about the center of a set of data. When I ask you to find the mean temperature, I'm asking you to find the balancing point or the general temperature that kind of binds all of the groups together in the middle. The median value is always the value in the middle, and the mode generally gives us clues about the value that is occurring the most. Standard deviation we call a measure of spread. Because the standard deviation, which I'm going to teach you about, tells us how the data is spread apart. It's not telling us information about just the middle of a piece of data. It's telling us how far apart the data spreads. Okay? So standard deviation describes by how much individual data points vary from the mean. So it's telling us how far data points are from the mean. We can say that a piece of information or a set of data is less variable if it has a small standard deviation. I want you to think of an example. Let's say we measured the heights of an NBA team. Maybe we measured the heights of all the players on the Boston Celtics. Now, in a basketball team, most, if not all of the players are going to be very, very, very tall. There's not going to be a lot of short people, right? So if this mean height, let's say, is 6'7" or 6.5 feet, then most players are going to be around that data, and there's not going to be a ton of very short players or a ton of very small players. Most of the basketball players are scrunched very close to this very average high height. But now let's say that we take and measure the heights of everybody at CCSC. We're going to have a large standard deviation, meaning that our mean height will probably even be lower than the NBA players' heights. Maybe the mean height is now 5.5 feet. But we're going to have some 6th graders that are really, really, really short. And we're going to have some seniors and some teachers that are really, really, really tall. And so our data is spread out further. We say that this is more variable. we say that this is less variable. So if your data is scrunched in really, really close, you have less variability. If your data is spread out further, you have more variability. All right, let's continue. We're going to wrap up by talking exclusively about the normal distribution. So we're only going to focus today for the rest of this lesson on this first normal distribution. A normal distribution can be modeled with a normal curve. A normal curve. And data with a normal curve, in other words, data that are normally distributed, these mean the same thing, follow these rules. 68% of the data are within one standard deviation of the mean. So let's think back to measuring the heights of everybody at CCSC. If the mean height is here, let's say the mean height is 5.5 feet, and if we move one standard deviation over to the right side, so one standard deviation above the mean height and one standard deviation below the mean height, then we've captured 68% of the people at CCSC. Okay? 95% of the data are within 2 standard deviations of the mean. So in our measure of CCSC heights, if we move 2 standard deviations away from the mean height, then now we've captured 95% of the people. So everything, for example, let me backtrack a bit. Within one standard deviation, whether it's above or below the mean, we have 68% of people. When we move 2 standard deviations away from the mean, we've now captured 95% of the respondents of our survey, of our heights. And you can kind of guess it, you would capture almost the entire set of our population, 99.7% of the data, within 3 standard deviations of the mean. So if we move 3 standard deviations of the mean, we've now captured nearly our entire school within the data, 99.7. So this is still pretty abstract because all you're hearing is 1 standard deviation, 2 standard deviation, but you don't really know what that means. So we're going to wrap up with a very concrete example using weight, okay? So in a group of people, the mean weight is 145 pounds and the standard deviation is 13 pounds. Fill in the missing values for the normal distribution. Well, in any normal distribution, the peak represents the mean. So the mean is always the middle. And I'm telling us that our mean is 145 pounds. Okay, our first distribution, our first standard deviation is going to be 13 pounds above 145. So if we do 145 plus 13, we land at our first standard deviation, which is 158. So our first standard deviation is 158 pounds. Now the standard deviations can go above the mean, but they can also go below. So we're going to take 145 and then subtract 13. And we get 132. Okay? That's our first standard deviation. This is plus 1 standard deviation. This is minus 1 standard deviation. Let's go ahead and plot our second standard deviation. Well, to do that, we just add another 13 pounds to this first standard deviation. So I'm going to do 158 plus 13, and I'm going to get 171. This is now 2 standard deviations away from the mean. If we can go above, we can also go below. So to do that, I'm going to subtract 13 from 132. I get 119. And this is now 2 standard deviations below the mean. Lastly, let's plot the third one. To plot the third standard deviation, I'm just going to add 13 again to 171. Okay? What we have is 184. And we can also subtract 13 from 119, and we get 106. So that's 3 standard deviations below the mean. Okay, so now this makes a little bit more sense. Below here we have the weights of different people, and here we have the standard deviations away from the mean. So if we now take into account all of this, basically what we're saying is that 68% of all of the people weigh between the first standard deviation. So they either weigh between 132 or 158. Because these are the first standard deviations above and below the mean. So we don't even know how many people we surveyed, but we know that 68% of them weigh between these 2 pounds. Next, 95% of the people weigh between the second standard deviations. So now we need to see what the second standard deviations are. Below the mean, it was 119 pounds. And above the mean, it was 171. Again, we don't even know how many people we surveyed, but we know that 95% of all of the people in this data set will weigh between 119 and 171 pounds. Lastly, this is a fill in the blank. We know that 99.7% of the people will weigh up between 106 and 184. And that's because that's the third deviation, the third standard deviation. Okay, so we're now, if we include all of this data, this holds 99.7% of our data. To wrap up, I'm going to just put up one random thought experiment. Let's say we took the mean or the weights of another group of people. Maybe it was even the same number of people. But suddenly our curve looks like this. Maybe the mean is actually still 145. But now our standard deviation is actually just 3 pounds. So that would mean that our first standard deviation is at 148. Our second standard deviation going up would be 151. And our third standard deviation would be 154. Below, we would just subtract 3. So one standard deviation below would be 142. 2 standard deviations would be 139. And 3 standard deviations below would give us 136. My question to you, and this is the last question I'm asking before this video ends, is which of these 2 curves is more variable? Is it this one with a standard deviation of 13 pounds, or is it this one with a standard deviation of 3? Well, we just go back to our definition from a few sheets ago. We know that our data is less variable with a smaller standard deviation and more variable with a larger standard deviation. So in this case, that means that this curve is more variable and this curve is less variable. And you can even see that. Most of our data is scrunched in really closely here, so this is less variable. There's less variety of weights, whereas here, the data is really spread out, so you have more variety of weights. That wraps up this lesson. Thank you for watching.